from the heart of Dubai, where tomorrow is being built today, to the world. Welcome to the CTO Show with Mehmet. Here, we redefine technology and reimagine possibilities. With Mehmet, delve into the riveting realms of AI, cybersecurity, and digital technology. Experience the thrilling highs and lows of startups. Immerse yourself in the spirit of entrepreneurship and witness the future of business innovation being written in real time. Now, without further ado, let's tune in and explore the future.
Hello and welcome back to a new episode of the CTO Show with Mehmet. Today I'm very pleased, joining me from Australia, Dario Valenza. Dario, thank you very much for being with me on the show today. The way I love to do it is I keep it to my guests to introduce themselves. But just I'm gonna give a disclaimer to the audience, like you are in a area which is very, very interesting. We didn't discuss it on the show before, but I'm gonna leave, the intro for you. So tell us about you and, your company, and then we can take it from there.
Yeah, my pleasure to be here. My name is Dario Valenza. I'm the founder of a company called Carbonics. We build long-range aerial data solutions, which is a fancy way to say long-range drones for photography and scanning of infrastructure and critical assets. My background is I've come to drones a bit of an unusual way. I come out of yacht racing, and particularly America's Cup yachts. And there's some technology that was developed in that environment, which I've spun out and adapted into the basic airframe of a drone, and then built a company around the operation of those drones in a commercial environment.
Cool. Again, thank you very much, Dario, for being with me here today. This journey is really, I would say, interesting. So what have attracted you to be in this drone area, like coming from designing racing yacht to here? So what special was about UAV technology?
I think that the timing is part of it. The convergence of the various different enabling technologies that make it possible. And that missing piece of the time was a lightweight airframe. So when you think of an aircraft, the airframe is the thing that holds everything together. It carries the payload, which is the thing you actually want to carry, the camera, the passengers, whatever it may be. And then everything else, the propulsion, the control systems, the avionics, all has to be as light as possible to allow range and efficiency. And as I was saying, the missing piece, the carbon fiber airframe, being able to make that lightweight and efficient enables the range and the economies that we're able to get out of our drones. So bringing that to the table and then putting together a company structure and a team that is able to rapidly develop and integrate and come up with something that will solve a real world problem was really the fascination. Having come out of racing, which is an environment where you have some artificial rules, but you have very clear goals and finite resources and time, that maps very well onto a startup where same thing, you have clear goals, finite resources and time, but you're applying it to solve a real world problem, which actually makes a difference to a market or a broad range of people as opposed to just having fun racing.
Absolutely. Now, just out of curiosity, before I gonna ask you the second question that I have prepared, who would be your clients, Dario?
Yeah, so mainly linear infrastructure. So that means power network operators, open cut mines, potentially power lines, railways. Really, where we come into our own is covering long distances in a single flight. So just for context, the aircraft can carry upwards of 5 kilos, which is sufficient for a high resolution scanning LiDAR combined with a fixed camera or a video camera. And it can do so for in the order of 8 hours, which means you're talking hundreds of kilometers in one flight. And being able to do that in one flight means you're not having to relocate ground equipment, you're not having to have people out traveling or actually in the air. And that's really where we get our economies of scale. And so we looked at a few different markets. We've done stuff in agriculture. We've done wildfire monitoring and prevention. We've done some stuff for security and military. But the linear infrastructure is really the low-hanging fruit for us because we can solve a real problem at scale. You can have few customers that have big needs. So geographically, there'll be a power line operator that might cover literally thousands of kilometers. That's one customer, but they'll keep you busy for a while. And so really our job is to replace what is currently being done with crewed aircraft, with helicopters and fixed-wing aircraft, do that cheaper, more efficiently, smaller carbon footprint, safer. We can get down and fly low and slow over the assets, and we can scan and photograph and effectively feed the data into a digital twin. That then allows more informed operations in terms of maintenance, things like vegetation encroachment, making sure that the trees aren't getting too close to the lines that could potentially start a fire, pole top scans to make sure that the timber poles aren't rotting from the top. So it's really providing information for infrastructure operators to really get the best out of their assets and operate them safely and efficiently.
Really interesting. And, when I hear these terms, doing things more efficiently, cheaper, especially, in some, I would say, verticals that are currently people, they don't think how much such innovations like the ones you have done, Dario, is important, from industries like whether it's the energy, whether it's like agriculture and all of this, because I was checking the website before we started and, immediately I saw the benefits of such technology. But, what I want to, get from you now, because, when we talk about such technologies, the design comes first, to us, like, because it's about the design. And I know, like, you like to apply first principles problem solving, right? So can you walk me through how much, the first principle problem solving, first, when the first time have you encountered and how you have utilized it now with your current company, Carbonix?
So I guess encountering it, there are lots of instances, in particular, just because that's my experience and my perspective, it doesn't mean it's the only place where it happens. But looking at yacht racing, the idea of doing everything you can to make your boat a little bit lighter, a little bit faster, a little bit more efficient, requires a lot of data. So you're looking for feedback. So you'll modify something, you'll go out racing or you go out testing, and you will measure whether the thing that you've done has made a difference or not. And the first principle thinking is you're not doing it by analogy. You're not saying, well, the other guy has done this, so I'm going to do the same thing, because then you're necessarily replicating. What you're thinking is, if I took this other thing from, material from aerospace as opposed to sailing, or something out of motorsport, or something that was developed for an analogous application, and I reduce it down to its fundamental properties. So carbon fiber is a good example, right? It's a composite material. It can be formed in very arbitrary and organic ways because it's molded. It has particular properties in terms of weight and strength. And rather than saying, well, it was applied this way over here, so I'm going to apply it the same way, you can think, what if I change it in this way? What if I combine the fibers with a different matrix? What if I change the angles? What if I change the thickness? What if I connect it with like a rigid piece of carbon with a soft sail? And come up with how those fundamental properties of the material will actually affect performance. So that's the sort of first principle thinking, where you don't look at an item in terms of its intended use. You look at it in terms of its fundamental properties. So it's like that. I think there's a famous exercise in team building and psychology where they give you a bag of items, or like a hammer and a nail, and you're supposed to list how many uses there are for that thing. So you look at a hammer and it's like, okay, its purpose is to hammer nails, but you could also use it as an electrical conductor, as a weight, as a plumb bob. There's different ways you can use the same thing if you take away that first layer of this is what it's meant for, and this is what everyone else has used it as. So examples, again, in sailing are really around material use, around engineering, around tuning, and also around rule interpretation. So there are countless examples in racing and similarly any technical sport, Formula One as well, where a rule is written in a way to prevent or constrain or give a particular outcome. But when you actually look at the letter of the law or the letter of the rule, it will actually be able to be interpreted in a way that was totally not what the writer of the rule intended, but is allowed. And that's how you get development. You get workarounds, whether it's a different shape or a different solution. And that workaround can give an advantage. And so approaching the rules with that first principles thinking was very formative when I was learning the trade and being part of racing. So there are a couple of examples. Then when you come to Carbonics and the drones, I guess it's putting together all these various enabling technologies. So saying there is this problem of data capture, there is the value of having good information. You could see that people were already starting to adopt multi-rotor drones because they're relatively cheap, they're easy to use, they're small, and you don't need a very sophisticated level of training to be able to use them. But they're limited in range. You can only cover so much ground with them. So thinking, okay, if these things could cover more ground, they would give you more value. And the only thing really that could do that at the time, 10 years ago, was a military drone, which might have cost millions of dollars. So to say, if we could create a platform that could cover that distance, that would be useful. Obviously, the requirement is it has to be lightweight and efficient, and you do that with materials that have those properties, and hence the carbon fiber. But then you start looking at how do you control it, how do you power it, and it's not at all obvious that you can buy off the shelf a control system and a propulsion system and a radio system that's designed specifically for that application. So there's a lot of improvising, there's a lot of adapting, there's a lot of taking stuff that is meant for something else and creating an interface board to translate one signaling language into another, making them work together, because then you get the best of both worlds. And having that approach at a level of the culture of the business, so that the engineers think in those terms and you're encouraging that, allows you to solve problems in very creative ways.
I love that because, there's this famous illustration on the internet where someone tries to bring the wheel and people, they're pushing the stones and because they're saying like, this is the way how we have done it all the time. I'm a big fan also of this principle. And, whenever I hear this phrase, if I ask people, okay, why you're doing this? And they tell me, yeah, this is how we found the people before us doing it. And we're fine, immediately it triggers me. And I think another example came to my mind, there's plenty of people who applied the first principles problem solving, across the different industries, and really people were not believing that they will succeed, but again, they did it. Now, you combine this, Dario, with something which also I'm personally passionate about, which is design thinking. Mm-hmm. And you do this in a field which someone would say, design thinking in aerospace, right? So how do you balance, the aesthetics, functionalities, and at the same time, the efficiency, and delivering, these benefits that you talked about, in an area where people, the first thing that comes to their mind may be, why I would apply design thinking, and design thinking is about, thinking with empathy, right? So I'm curious to know your point of view on this.
Mm-hmm. It's interesting on the idea of always doing things from first principle. I think you have to balance that against valuing lessons that have been hard won in the past. So just because something's been done a particular way doesn't mean it's wrong, because there could be very good reasons for it. But part of first principles thinking is evaluating that. So saying, well, this traditional way of doing things works and it has these pros, it might have some cons. Can I address those cons by changing something? And there's something to be said for evolution, where you have more data points on something that's been done than on something brand new. So when you do try something brand new, you have to get that data somehow because it is not there from previous iterations. And so you have to be mindful of that and find a way to validate the first principles idea, because it may actually not be as good as the traditional way. And doing that well is really the balance. When you say design thinking, I think of it in terms of almost abstract. It's really designing the variables and the requirements and meeting them, and then the thing kind of shapes itself within those bounds and constraints. When you look at the outer shape of the aircraft, that is really purely aerodynamic. And so if you look in nature at birds, they are elegant because they have adapted over millennia of evolution to do a particular task in a very efficient way. And because they move through air, they're necessarily, graceful curves and continuous, and they've got fillets and they've got details that look as though they would work well in a fluid, and that makes them sleek. And so learning from that and applying it to an aircraft design where you have the freedom in the materials to come up with those shapes. So if you look at, an aluminium airliner, you're sort of limited by production methods. You've got aluminium sheets that you can only wrap around so much. It makes sense to make things straight because it's easy to fabricate, to replicate. When you move into composites, the mold can be any shape because it's just carved out by a CNC machine. And so you can make complex curves. You can have twists in the wing. You can have taper. You can have curvature. You can have fillets where it meets the fuselage. And if you have the freedom to do that, and if you have the tools to simulate the flow around such shapes, then you can optimize more. So it makes it more beautiful, but that's a byproduct of the functionality of the fact that it's interacting with the air in a better way. And then because the material is strong, you can make the wings thin, for example, and then you have the elegance of very thin, very delicate looking, sleek shapes, which are actually quite strong and robust, and react to forces in a way where the more they're stressed, the better the shape becomes. But that's really the visible side. When you look at the design exercise, and that's sort of, I make a distinction between design and engineering, where engineering is actually specifying things, so getting down to the thicknesses of the sizes and the connectors and the wire diameters. The design is really the scheme. It's saying, it's the diagram. And for an aircraft, it's a packaging exercise. So you have to carry the payload. It has a certain mass and a certain size, and you can't really change that. So the aircraft kind of develops around it. The volume that the payload needs is basically the diameter of the fuselage. Then you try and package in there the avionics, the autopilot, the batteries, the wiring, and you want to squeeze it all together in a way that it fits in the smallest possible envelope so that it makes a smaller hole in the air and has less drag. But you also need it to be accessible, to be maintainable. You need to be able to open it, to get in there, to swap things out. So it's really this balance between the optimum aerodynamic shape, the tightest packaging, and other requirements such as how to get in there, maintenance and all that. And the design is balancing all those things. So design thinking is, this is the mission I want to do. This is what I want to carry. This is how far I need to carry it. So this is how much fuel I'm going to need. To keep that all in the air, I'm going to need so much propulsion, and I'm going to select this engine. And then I put it all together in a way that it makes the tightest, thinnest, sleekest package to do that job.
Very interesting, I would say, way of thinking by itself, if I want to put it this way. You just mentioned something, which again, it brought a question to my mind. Honestly, I didn't prepare for it before, but because you mentioned, the aviation industry. I mean, the traditional aviation industry. And maybe it's not related to exactly what you do, but just because you're now into this space for a long time, why do you think there was no real, I would say, disruption in the aviation industry? I mean, of course, on the manufacturing part of it. Like, of course, we've seen beautiful aircraft. I mean, design, but at the end of the day, yeah, like I feel this bulk feeling, like it's like something which is on a assembly line, and like I don't see really something that, oh wow, like this is the plane of the future, or like this really. Why do you think we get stuck in that? And I know like maybe it's not your field in I mean, you're more into the drone space and UAV space, but as someone now closely watching that, what you can tell us?
It is really interesting. And when you look at evolution, like in the 60s, we had the 747, we had Concorde. There was this trajectory where things were going to get better and faster and potentially cheaper at scale. I think there's a number of factors. We reached a practical limitation on propulsion. So, jet engines, you went from a pure jet to a turbofan. The fans got bigger, but essentially it's the same technology. There was a long learning curve to refine them and make them reliable. So if you look at, it was very common to have 3 or 4 engines until not that long ago, maybe the 80s or the 90s. And then we were able to have twin engine aircraft because the reliability of the engines was such that the risk became acceptable to not have a third engine. And so that then drove some efficiencies, and it actually made all the designs converge, because first you had 3 engines at the back or 2 engines on each wing or all these weird arrangements. Now you just have an engine on each wing, and that's pretty much the standard design. I think in aviation, particularly where you're carrying people, you have to reach such a high standard or burden of reliability, and that's driven by regulations as well as the companies themselves imposing those standards, that the development cycles are just so long. And the investment to create a new airliner to meet all those requirements is enormous. And it's very easy to take something that's already proven and tweak it and improve it, make it a bit longer, make it a bit bigger, put better engines on it, put composite control surfaces on it without changing the structure. So the cycle's getting longer. That safety standard dictates that there's a lot of testing involved. The risk reward is such that if you try something new, it's a massive investment. You may not see the returns for a long time, and if it doesn't work, it could break a company. So I think part of that is just the physical limitation of propulsion, the regulatory burden that you have to meet, and the fact that the materials technology at scale didn't really change. So when you went from, timber construction to aluminium, it took 30, 40, 50 years for aluminium airframes to become something that you can stick on a production line and churn out at scale. And that got automated, and you got robots in the production line. And to do that with carbon fiber, to go from small hand-laid, labor-intensive structures that are basically one-offs to something like a 787 where you have a barrel that's filament wound by a robot and just gets made in a matter of hours. There was a lot of work that had to go into that. And so again, the development cycle was very long. And then you look at the economics, the fact that it appears that most people don't really want to pay a premium to get there sooner. And so something like Concorde, the cost of the fuel and what it takes to go that fast doesn't seem to scale linearly with the ability of the market. So when you look at airliners, they've actually got slower rather than faster, as well as, the queue at the airport is longer, there's more security, it's more crowded. So that premium on getting there as soon as possible has kind of gone away. And people are connected so they can work while they're waiting and all of that. So I think that's influenced it. in a way, it is a bit sad. It could be great to see faster, sleeker, cheaper aircraft be developed, and I think over time they will. But I think aviation is sort of necessarily slow moving because of the safety involved, and to get it at scale. And I think drones is a space where you can move more rapidly because the requirements are not quite as stringent. But again, our aircraft is 50 kilos. So it's something that you do have to take seriously. And the safety case around that is also quite strict. And part of the design thinking is how do you build that in? How do you design the thing so it has redundancies at the fundamental levels? It's got 2 propulsion systems, 2 of everything, and very few interdependencies. And how do you develop operational procedures, safety checklists and things that will support that operation? And that also takes time. And part of our moat, I guess, as Carbonics, is the fact that we've gone through that exercise, and that necessarily takes time. But once you've invested that time, then you're able to go and play while someone else has to go through that again.
Absolutely. And I'm really happy you shared these details with us here, Dario, because some people, they think it's easy, but you mentioned something crucial, especially about, because we're carrying people and you have like this responsibility also, and the regulations. So it's not like something you can change overnight. It takes years and years to be able to come out with design that is approved also by the authorities around the globe for making this fly. Now I want to go one step back and focus again on the UAVs and the drones, and because you when you were explaining about the first principles, right? So you mentioned about like there are different components. So if I want to focus on the technology parts, Dario, like there's a lot of things which are okay. The drone is what we see flying, right, or the UAV, but we have plenty of things, technology related on the other side. So aside from, of course, the communication protocol, so what other like major components are there? And I'm asking, maybe it's like a basic questions, but just to enlighten also the audience about the technology part of the UAVs, other than of course the mechanics of the drone itself.
So it's a system, and the system comprises the aircraft that's flying and carrying the payload. As you mentioned, the communication, so being able to talk to it over long distances, and that can be direct if it's a radio, or it can be via satellite or via cellular, and we generally have redundancies on that. And then on the ground, we have what we call a ground control station. Now that can either be like literally a computer in a box that sits in the field, or it can be a remote operations center, which is a room with some screens where people sit and watch the aircraft fly. Depending on what we're doing and how we're operating. The remote operations center means that you can actually do what we call remote one-to-many. So you can have several drones flying in different places, and you can have a central control center that supervises them. To do that control center itself has to have redundancy. So you have to have a uninterruptible power supply, several different means of connecting to the internet, security around the door, there's another person there in case something happens to the pilot on duty. There's all these things that you have to think through to say, okay, I've got this room where I'm virtually in the cockpit of the aircraft, but I'm actually not there. I'm doing it virtually. And you're not necessarily getting what we call a first-person view, which is like a camera on the aircraft that's showing you what the aircraft is seeing, but you're flying on instruments. So you've got a map, you've got the position of the aircraft on the map, you've got readouts from all the various instruments to tell you that all the systems are functioning optimally. And so really they're the two components. There's the aircraft that flies and there's the ground control station. In our case, the aircraft flies an automated mission. So what we do is spend a lot of time before we fly planning the flight. So we put in waypoints. So wherever the aircraft has to make a turn, there's a waypoint. It'll fly to that waypoint, then turn to the next one. And those waypoints are three-dimensional, so they're X, Y, and Z location. And then we'll plan what we call alternates, which means if something goes wrong, come home or go and land in this other grid-approved safe location. And we design that mission, we run it through a simulation, we test it, we make sure it's clear of terrain and things like that. That gets uploaded to the aircraft, and then the aircraft has that in its memory. So when it takes off, it will just execute that mission, even if it doesn't have connectivity or any intervention from the human. Now, because we want to be able to communicate with it, if it loses connection, it'll go to an alternate or it will land. But the job of the pilot mostly is to supervise the aircraft and only intervene if something goes wrong. And so when you then go one level up, the system is the aircraft, the ground control station, and the network that it's a part of. So we'd have ADSB, which is effectively a beacon that signals the aircraft's location to other locations, and the procedures and the preparation that you do beforehand, the stakeholder engagement, the monitoring of the airspace, that's all part of the system to operate the drone.
That's fascinating. Can they be autonomous in a sense that, for example, let's say while the aircraft is flying, a bird comes in phase, like it can maneuver? I believe it can do these things, right?
Yes, eventually. I think at the moment it's quite basic. And I think people are surprised at how hard that is to do. So if you think of self-driving cars, they've always been 5 years away for the last 20 years. And it's easy to get to 80%, but that last 10% is really hard. If you imagine the drone's flying, and it sees another aircraft go past somewhere nearby, you're recognizing an object that is far away and against either a blue sky or a mottled background with trees and stuff that's very hard to resolve. To do that visually, to actually understand, is it a small object that's close? Is it a big object that's far away? Is it going to cross my path? What direction is it going? You require very high resolution cameras. You need sort of binocular vision. You can do it with LiDAR, but then you've got a lot of clutter and noise in the background and you don't have that much range. You need heavy instruments, you need a lot of computing. So really, yes, you can have it at a basic level, and over time it's going to get better. And part of the product roadmap for us is adding that level of automation. So now that we've got a proven platform, a system that works and is robust, over time we will add that. Right now it's not stopping us from doing the missions we need to do over power lines, because generally we make sure there's no air traffic around. But it's a challenge. It's something that's there are companies out there developing machine vision and detect and avoid and things like that. What we use at the moment, like with ADSB, if the other aircraft has a beacon, then we'll know it's there. And so in what we call instrument flying rules, so whenever at night or in bad weather, only aircraft with that instrumentation are allowed to fly. In visual flight rules, where people can go with their ultralight or their Cessna or their farm helicopter, and they're relying on just using their eyes to see what's around them, that's actually more dangerous for us, because you're really then relying on that see and avoid without instruments. And so part of what the various aviation authorities are doing around the world is working very hard to encourage all aircraft to have these beacons, because they're going to need those if they're going to share the airspace with drones. And so there's all this thinking around, as drones integrate into airspace, we can't reinvent the way airspace management is done, because it's very well established and very robust. But we do have to make allowances for drones, because they are going to be part of airspace, and working out how to do that optimally is really interesting.
Yeah, it's very interesting space to watch indeed, because even we have seen actually people who tried to do this in bad intention, I would say, to fly drones near airports and things. So yeah, like this is again a regulatory component within the drones. But what I was interested about is, because here we're talking about like every factor that when I think about edge computing and like a kind of IoT setup, so the drone has all this because it can have the sensors. of course, with a 4G connectivity and maybe probably a satellite connection. I don't know, like because on the planes now we can have this. So I assume we can have the same thing on the drones. So like it can give real time data to the ground station, and this data there can be analyzed, done something with it. And I'm sure like what you do today, and you explained this at the beginning, so you can collect this data and then it can be again pushed to a central analysis
Process,
plane,
yeah.
right? So because what I've seen in drones, Dario, like it's very interesting because first it allows us to go places where like us humans physically we cannot, right? So we cannot reach. And the second thing is it can act as our eyes and ears as well, because it can collect this amount of information from these far places. And then because I'm fanatic about data in general and collecting data through sensors, so this is why this brought this question to my mind. So how do you envision the next generation of drones to be like? What's the future hold for us for drones?
I think the cliche there is dirty, dull, and dangerous. So any tasks where it's boring, it's potentially dangerous, or it's dirty, people don't want to do it, that's where automation can really make life better. When you ask about drones, the thing I like to say is that it's a very broad term, right? You've got drones, everything from micro drones that you can sort of throw up in the air to spy on people, to cargo drones, to eventually automated air taxis that are sort of a drone. And we're seeing this sort of Cambrian explosion, this proliferation of different configurations. Like if you think about a multi-rotor, like a little quadcopter, not very long ago, it would not be possible to stabilize a platform like that because it just didn't have the compute, so that the PID loops that could work quickly to stabilize something that's inherently unstable. You didn't have the power to weight ratio in the electric motors. You didn't have the energy density in the batteries. You didn't have the ready availability of solid state gyroscopes that can measure the pitch and the attitude. So all those things had to happen for a flying machine of that shape to actually fly. And now if you buy a relatively cheap off-the-shelf multi-rotor and you look at it fly, it looks supernatural. Like it is just rock steady. It sits there, and it has respectable half-hour flight time. So without high energy density batteries, without high power density electric motors, without solid state gyroscopes, without Wi-Fi and sophisticated radio links, without the software and the PID loops, without any one of those elements, that couldn't exist. But now that it does, you have complete freedom on the configuration. You can build a drone that looks like anything. And you go online and people make them, they look like a cat or they look like a Halloween decoration, and they don't care about aerodynamics. They can stabilize themselves, they can fly. And so that has opened up the door to drones that carry spare parts, organs, go and put out fires or burn things off power lines. You name it, someone's built a drone to do it. And I think a lot of those applications will not scale economically, and some will. And so the future, again, the space where we play in, so covering hundreds of kilometers to take very high resolution data over critical assets, I think that's now going to be an evolution where we've got the vertical takeoff, we've got the platform, we've got the functionality to be able to go and do the mission. Over time, we will add automation, we'll add redundancy, we'll add regulatory robustness due to just putting hours on the aircraft. So right now, we're able to fly over low population densities, but we couldn't fly over the middle of the city because it's still considered too high risk. Over time, as the hours get accumulated and the robustness of the system is proven and more automation is put in place and redundancy and airspace management, we'll be able to fly anywhere. And that then opens up the scope to do even more. And over time, as batteries get more energy dense, as the motors get better and potentially things like hydrogen come online, you'll just push that further. You'll carry more weight for longer. And that's really where we want to play. And then it's just a matter of getting into that business as usual cycle for the utilities, for the mines, for governments, for firefighting, where they understand what this thing can actually do. And it finds its way into their processes and it just becomes part of their toolkit. And that's how we scale.
Cool. Dario, like as we're almost coming to the end, I gotta ask you something not related to drones, actually related to you as a founder, actually. I spoke to a lot of founders in different fields, but your field specifically, it's not easy, right? So it's not easy to be there. And you've been like, Carbonix is, I think, 10 years old now, right? So, and almost 11, as I can see. This journey, as an entrepreneur, right? You wanted to take, your experience in racing and yacht designs and bring it to something you are also passionate about. But I mean, from a founder perspective, I'm sure like there were plenty of challenges that you have crossed, and I'm sure like you can share some of them so other founders, even not related to aerospace, they can learn from that. So I would love to hear like a couple of these challenges that you were able to overcome.
It's an adventure. Yeah, I mean, looking back, first of all, you can't know going in what it's going to be like. And I'm sure everyone has their own motivation. In my case, it was about maintaining that interesting work environment. So I, fortunately for me, never had a proper job or an office job. I was working on boats. I was doing interesting things. I did a stint building movie sets for a short time. I wanted to create an environment where we could have a small, tight team of very high performance oriented people doing some very interesting work that is new and challenging. And that all sounds fantastic, but it has to be funded, so it's capital intensive. And you have to have the clear vision and be able to communicate it. So for me, when you start off, it's all fairly small and fairly controlled, and you tell people about it. And you might make sense, but human nature is such that they think, well, this guy's great, but he's never done it before. So is he going to stick around? Is he going to make good on his promise? Is he going to be able to handle challenges? Is he going to have the stamina to see it through? And that's the hard part. It's really getting that buy-in, that the first 1, 2, 3, 4, 5 people that actually share the vision, that say, well, this is actually worth doing. And when you look back and you think, we've got a team of 25 people, these people are devoting the peak of their working life as experts, as leaders in their field, to this vision. And to have that buy-in and to see that being carried forth by other people is really the sort of the validation. It's saying it was an idea, you put it in front of people, you led by example, other people saw it, they came on board, and then they added their own contributions to it. And it changes and it evolves, and everyone brings their own contribution that then takes it in a slightly different direction. But getting that buy-in, getting that coherence in the team to all believe that this is a worthwhile exercise is really the challenge and the reward. And the thing that then makes it continue, because it sort of gets a life of its own. Like, obviously, it's still, as a founder, you think you're always necessary, but I think the business gets to a point where it actually functions perfectly well without you if you've done your job correctly. And everyone's on the same page, everyone's aligned, values. And again, I hired a CEO as soon as I could because I wanted to be involved in the tech and in the vision and not necessarily in the day-to-day running of the business. The set of skills that the CEO brings to the table is necessarily different. It's organizational, it's commercial. And our CEO brought these values into the business that are aligned with what I wanted to do, but they have, not his spin, but his angle. And, that actually complemented and sort of supported what I wanted to do, but in a way that was different to how I would have done it. And that actually gives you that, diversity, for want of a better word, that brings more resources to the table and more options in how to solve problems and how to go about things. So it's really, you start with a vision, you create the environment, you bring people in, they buy into it, and then they run with it.
I love that, Dario. And to your point, I've always seen, and I think you just nailed it actually, and I don't have to give you this as a compliment because you've been doing this for a long time. But I mean, the people, and I appreciate in you, Dario, accepting that you wanted to be on the technology side of the things and bringing, someone to run the business. Because what I have seen, majority of the time happens, people, they are brilliant in the technology, in design, but they keep saying, no, I would run also this business. And I've seen them burning out, and, then, they get pushed out of their companies, unfortunately. And we see this a lot in the startup wars. But, I think, you have, this, and I can feel it, during the conversation today, your clear understanding of what you want to do. And, you've put your ego aside, as they say, and you just focus on the mission and the vision of the company, and you brought everyone in. So really, this is a great example for how things should be in the actual world of startups, I would say. Dario, final thing, where people can get in touch and get to know more about you and, of course, about Carbonix.
Yeah, probably the easiest way to get in touch with me is through LinkedIn. Just look up my name. And then Carbonics is through www.carbonics.com.au, which is the Australian domain name. And all the information will be there about making inquiries and all that. So just go to the website.
Great. Sure. I will make sure that these are in the show notes if you're listening on your favorite podcasting app, or if you are watching this on YouTube, it will be in the description. Dario, again, thank you very, very much for your time today. I know it was a little bit late for you as you're in Australia and I'm in Dubai, so there's this time difference. Thank you again for, all the insights, the experiences, and of course, the way you explained to us today, the technology and, your motivation, your vision behind it. So, and the use cases. So this is really something really valuable. I learned a lot personally from you today. Thank you for sharing that. And as always, this is how I end my episode. This is for the audience. If you just discovered our podcast by luck, thank you for passing by. If you enjoyed this episode today, give us a thumb up, subscribe, and share it with your friends and colleagues. And if you are one of the people who keep coming back, thank you for doing so. Keep sending me your suggestions, questions, comments, and so on. I really appreciate every single feedback you send it, whether it's about something good, something bad. Don't hesitate. Reach out, and I would love to get in touch with you. Thank you very much for tuning in, and we'll meet again very soon. Thank you. Bye-bye.
Thank you.
Hit that subscribe button. Share the show with your tech-savvy friends and fellow entrepreneurs. And leave us a review on your favorite podcast app. Your support means the world to us.